Okay, we're now moving on to the major focus of today's lecture, and that's Chapter 14, the acid-base equilibrium. Now, there's going to be a couple of definitions for what an acid is and what a base is, but the most commonly used one is that developed by Johannes Bronsted and Thomas Lowry in 1923. And what they did is they focused upon the proton. So for them, the Bronsted-Lowry acid is a compound that donates a proton to another compound. And a Bronsted-Lowry base is a compound that accepts a proton from another compound. So what type of compounds are acids and bases? Well, first of all, acids, though, can be either an organic or an inorganic molecule. It's cations that contain a hydrogen ion or anions that contain a hydrogen ion. Bases are ionic compounds that contain an OH group. There's molecules or primary amines that can be bases. There's anions with or without a hydrogen ion or cations. And there's a few examples of those as well, just not as many. So in addition to something being an acid or a base, a species that's formed when a proton is removed from the acid is then called the conjugate base of that acid. So a conjugate base is an acid that has had its proton removed. Likewise, a conjugate acid is a species that is formed when a proton is added to a base. So the conjugate acid of that base is what has a proton added. Now there are some amphiprotic species, and protic here refers to protons, right? Species that can either accept or donate a proton. They're amphiprotic. An amphiprotic species can serve as an acid or a base. Water, for example, is one of the best examples of that. In the presence of an acid, water acts like a base. In the presence of a base, water acts like an acid. Here's an example. You've got water acting as an acid, and you've got your conjugate base over here, and it removes the hydrogen. So there's just the oxygen and the one hydrogen. Here's a conjugate acid-base pair. You've got ammonia, that's a nitrogen with three hydrogen ions on there. You add a hydrogen ion to there, and it forms the ammonium ion, the conjugate acid. So an acid plus a base gives you a conjugate base and a conjugate acid. Hopefully that's clear. So the reaction between a Bronsted-Lowry acid and water is called acid ionization. And here's an example of that. You've got hydrofluoric acid. Water is now functioning as a base, and you form this. This is the protium ion here, H3, or the hydronium ion here, which is the H3O+, and then you have the base over here. So a reaction between a Bronsted-Lowry base and water is called a base ionization. You see that here that the water is acting as an acid. Here is your base, and it is forming this type of compound right here where you can see that hydrogen has been added to this nitrogen. And now the OH forms that base. In pure water, water also acts as both an acid and a base. The equilibrium constant for this reaction is called the ion product constant for water, or K sub W. The key thing here is that, and this is a very important point, because this forms the whole basis for which we determine our measurements of acidity and basicity. At 25 degrees centigrade, K sub W equals 1.0 times 10 to the minus 14th. And so you can see here is your one water molecules acting as an acid, one is acting as a base, and then that forms the H3O+, and then the OH. So in pure water, K sub W, as we saw there, remember that's the concentration of the H3O plus and the hydroxide ion equals X equals 1.0 times 10 to the minus 14th. When the concentration of those are the same, the solution is said to be neutral. That is, it's the square root of that number that you have up above. So that is the square root of that, of course, is 1.0 times 10 to the minus 7th molar. And in pure water concentrations, and that doesn't happen very often, but in pure water concentrations, that would be your DI water, distilled water. The H3O plus and the OH minus are equal to each other. When an acid or base are dissolved in them, they are no longer equal. So that when you have that situation, these are inversely related to each other. In the situations where your H3O plus is greater than 1.0 times 10 to the minus 7th, then the OH has got to be less than that, right? Because the two of them have to add up to that, or have to be multiplied together to be that. And the solution is called acidic. Likewise, if the OH is greater than 1.0 times 10 to the minus 7th, the solution is called basic. Now, working with those exponentials is sometimes a little difficult, and so what people have done is they've developed what they call a pH scale. That's a small p with a capital H. And the acidity is based upon the logarithm of that concentration. So that the pH and a pOH is going to equal 14. And likewise, the pH of a neutral solution is 7. 1.0 times the concentration of each is 1.0, and that solution is neutral. Now, the greater than the solution, and that is that the pH is less than 7. That's what happens when the H3O plus is greater than 1.0 times 10 to the minus 7. The solution is acidic. And if that is acidic, then that means that the basicity would be less than that. And if it's that is less than 1.0 times 10 to the minus 7, then it's basic. So this is what, and as you can see from that how much easier it is if you look at it just in terms of pH. Acidic means at pH is less than 7. And the lower it is, the more acid that solution is. If something is neutral, pH is 7. Basic, pH is greater than 7. And 14 is the highest value that it can have for the pH. The lowest value you have is pH equal to 1. And so 1 to 7 is acid, 7 to 14 is basic, and 7 is where it is neutral. This is a list of some of the common acids, and it's listed in terms of the strength of the basicity of those particular molecules. So you have got water there, and then when you go higher, the hydrogen carbonate ion, hydrogen cyanide, ammonia, hydrogen sulfide, carbonic acid, acetic acid, all the way up to sulfuric acid and perchloric acid at the very top of that scale. So you are actually decreasing in pH numbers as you go from water at 7 all the way to perchloric acid and sulfuric acid, which are essentially 1. Likewise, on the base side, what you have are things that are going down in the other direction, right? You've got where the hydroxide ion is there, right? And all the other ones. So recall from chapter 4 that some acids are strong. HCl, HBr, HI, in other words, hydrogen with all the different halogens. The hydrochloric acid and the nitric acid, and the sulfuric acid. These acids essentially react completely with water. Recall as well as some bases are strong. That's the lithium hydroxide, sodium hydroxide, etc. And these bases dissociate completely into the OH ion. Now, these right here are different ways of determining. They're called the universal dye indicator strips, or ones that are used as a rough measure of the pH. So, remember our definition there. Brownstedt-Lowry acids are hydrogen ion donors. So the strength of an acid is measured by the extent to which it forms H3O plus in water. Strong acids yield nearly 100% of that ion. Weak acids much less. And so here we have 6 strong acids and 6 strong bases. Relative strengths of weak acids can be determined by measuring their equilibrium constants. That's why we went through all of that equilibrium concentration calculations in that prior chapter. And you can see we work out the equilibrium constant instead of just a K. It now has a K sub A to represent the acid ionization constant. The Ka values are relative to the strength of the acid. Now remember, the H2O in this is going to equal essentially 1, because that does not enter into the equation. You're going to have the hydronium ion concentration, H3O plus, in the numerator, as well as the A minus in the numerator. And it's going to be divided by the concentration HA. And the larger the value of Ka, in other words, the more that you have of things on the right-hand side of the equation, the stronger the acid is. The smaller that is, the weaker the acid. Likewise, you can do the same sort of thing in terms of the base. But instead of doing a pOH on these, we still use the pH for these and just go from 7 to 14. And the strength of the base is also measured in terms of the extent to which it forms the hydroxide ion. Strong bases yield nearly 100% of that ion, and weak bases much less. So here you've got the relative strength of the base are determined by measuring their equilibrium constants. Again, same exact sort of equations are involved. And here, the Kb, the larger the Kb of the base, the stronger it is. The smaller the Kb of the base, the weaker it is. Now this will be measured as pOH. Okay? So Ka and Kb are inversely related, because as one gets larger, the other one gets smaller. The larger Ka is of an acid, the smaller the Kb is of its conjugate base. The larger the Kb of a base, the smaller the Ka of its conjugate acid. The extent to which an acid donates a proton to water molecule depends upon the strength of its conjugate base. If A is a strong base, then any proton donated to a water molecule is recaptured by that ion. And so that means that little of the hydronium ion would exist in solution, and therefore it would be a weak acid. And if it's a weak base, it's unlikely for the HA to recapture a proton, and as a large amount of hydronium ion would exist in solution, and therefore it would be a strong acid. And this gives you the relative strength of acids and bases on these different ones. And let's pause there for this particular section and then continue on with the next slide.